It is my honor to introduce Sarah Terrell. She's going to be graduating this semester with a degree in applied mathematics, and then she plans to go on to graduate school in economics. So she was interested in coming up with a senior project that combines those two areas of interest. So with that, she's going to talk to you a little bit about the mathematics behind the board game Monopoly.
All right. So my project is entitled The Best Strategies a Player Can Employ to Win Monopoly. As Dr. Anderson was mentioning, I did decide to choose this as my project because it combines both mathematics and economics. We can actually think about the economy in Monopoly as a toy model of a real economy because it has all of the same basic structures that a real economy has, but it doesn't have all of the complexities that a real economy would have. So with that being said, I'd like to start with a little bit about probability theory. I use quite a bit of probability theory within my project, so I think it's important for you all to have a general understanding of what probability theory is and how you would go about calculating the probability of a particular event. So given a sample space S, where S contains different possible events, if we wanted to calculate the event of one of those if we wanted to calculate the probability of one of those events, we would go about it by finding all of the number of ways in which that event can occur within the sample space and then dividing it by the total number of events within that sample space, where the two following conditions must be met. One, the probability of an event must be a number between 0 and 1, and the sum of all of the probabilities of all the events within the sample space must equal 1. So with that being said, I'd like to move on to what's known as a Markov process. A Markov process is defined as a mathematical model which combines probability and matrices to analyze a process that evolves from one state to another where the element of chance is always involved. A Markov process then requires three characteristics. First, there must be countably many states. 2, starting at any state, you randomly change states where the state ended is only dependent upon where you started. And third, each row within the transition matrix must sum to 1. This I'll discuss on the next slide. So a Markov process always involves what's known as a transition and a state matrix. A transition matrix represents the movement between the different states. So for my project's purposes, the different states represent the various spaces that a player could land on the game board. So then the transition matrix explains where a player can move to within a single turn, starting from a single given space on the board. So to make more sense of this, if we're working with my transition matrix that I developed for my Monopoly game board, and we're working on the row that represents starting at the go space, what that row would contain is all of the possible spaces that you could land on, given the fact that you started from go. So basically what we're doing is we're breaking up a probability of 1 into all of these little different pieces that you could possibly land on given that you started from go. And so the next row within my transition matrix would then be the row representing Mediterranean Avenue because that follows go on the Monopoly board. And Mediterranean's row would then show all of the places that you could land on, that you could end your turn on, given the fact that you started from Mediterranean. And every single row within my transition matrix would have this same characteristic. So a transition matrix is always going to be a square n by n probability matrix where n represents the number of states and the elements of each row must sum to 1. So a transition matrix is generally going to have a form like this, where those p's are representing actual probabilities within the transition matrix. And then this formula down here is just saying that if you are on row I, all of the elements within row I must then sum to 1. So so then the state matrix then becomes a vector of size 1 by n, where n once again represents the number of states, and a state matrix always begins with what is known as an initial state matrix. The initial state matrix V0 and every other matrix that follow is a probability vector where all of the elements in the vector sum to 1. So for instance, if we wanted to find the next state after the initial state, which is represented by V1, then we would perform the following computation where V1 equals the initial state V0 times the transition matrix T that explains the movement within the game board. So basically what V1 is representing here is where a player could possibly be in the game given that one turn has occurred. V2 would be very similar. V2 would then represent where a player could possibly be in the game given that 2 turns have occurred. And V2 would be calculated in a similar manner, where V2 equals V1 times the transition matrix, or equivalently, the initial state vector times the transition matrix squared. So before I dove straight in, continuing on in that sequence, we find that this actually forms what is called a Markov chain. And we find that this Markov chain can eventually converge to a vector v if v ends up equaling v times the transition matrix. So to make more sense of this, let's imagine that we have a state matrix where we're representing m many terms, where m is a very large number of turns. If we ended up doing the calculation of Vm times the transition matrix, and we got Vm back out of that, we would know that in fact that the Markov chain has converged. And when it converges to this particular equation, we call that the steady state, where there is an eigenvalue lambda of 1 being multiplied by the eigenvector v. So before I began with Monopoly, I wanted to begin with an easier game, so I began with Chutes and Ladders. Chutes and Ladders is easier for a couple of reasons. Chutes and Ladders has a spinner that dictates how many spaces forward you can move, and that those spaces forward is 1 through 6. So we can think about this equivalently as a single die being used to dictate how many spaces forward you can move, where Monopoly uses 2, which automatically makes it a little bit more difficult. The second reason is that in Chutes and Ladders, you obviously have chutes and ladders that can take you to different places within the board game, similar to in Monopoly, where you have community chess and chance cards that can send you to a different place on the board. The Chutes and Ladders version is easier though, because a chute will take you to one spot on the board, or a ladder will take you to one spot on the board, where a community chess or chance card has the possibility of sending you to multiple different places or keeping you where you are. So these are the reasons why I began with Chutes and Ladders. So I started by developing my transition matrix, which ended up becoming a 100 by 100 matrix, where every row's elements sum to 1. The reason why it's 101 is because if you've ever played Chutes and Ladders, there are 100 spaces on the board game, but you don't actually start on space 1, you start outside of the game. So I had to create a start space in order for my transition matrix to work in the same manner that actual gameplay does. So then my initial state vector ended up becoming V0 equals 1, 0, 0, 0, all the way up until column entry 101. The reason why this is the initial state vector is because when you start the game, you have to start the game on the start space, and therefore cannot be anywhere else at the time that you start. So I went through the Markov chain process, and I did several iterations of it, and eventually found that it did in fact converge and stabilize, and I then verified that using eigenvalues and eigenvectors, where I solved that equation on the previous slide. And I found my steady state vector to be this, where v equals 0, 0, 0, 0, all the way up until column entry 101, in which we have a 1 there. So basically what this steady state is indicating to us is that as you take more and more turns in the game, it becomes less and less probable for you to be anywhere else in the game other than the final winning space. So basically what this is indicating is that Chutes and Ladders is not a continuous game, meaning that a player must eventually win the game given enough turns. And what I found through the Markov chain was that the shortest game of Chutes and Ladders can last 7 turns, and the longest game of it can only last 261 turns. So once I felt like I really had an understanding of how the Markov process worked, I went ahead and moved on to Monopoly. This is just basically a representation of the Monopoly board we have all come to know and love, just with my specific numbering system that I used within my transition matrix and my state matrix. So as you can see all the way over there, Go represents, is number 1, Mediterranean is number 2, and it continues onward until we get up here. I ended up breaking up just visiting and in jail into two different spaces because I think it's important to understand where you really are in the game. So then just visiting became space 11 and space 12 became in jail. And then after that, it follows the same linear pattern where St. Charles is 13, 14, all the way up in a clockwise fashion to 41, which represents Boardwalk over there. So I began developing my transition matrix first, and my transition matrix ended up becoming a 41 by 41 matrix due to what I explained on the previous page. And every single row sums to 1, all of those elements. What made this particularly difficult is I had to incorporate several different aspects of this game into the transition matrix, such as the rolling doubles rule. Most of you who have played know that if you roll a pair of doubles, you have to roll again. If you roll 2 doubles in a row, you have to roll again. And if you roll 3 doubles in a row, you are sent to jail, the in-jail space. So I had to basically think of all of those different possible combinations and then think of all of the probability and then think about the probability that's associated with that combination and where that combination could possibly send you. After that, I then went into figuring out the community chess and chance cards. As I said before, community chess and chance cards have the possibility of sending you to multiple different places or keeping you where you are. So when you're dealing with one of those entries that represents a chance or community chess space, you have to break up that probability into all of the different places it could possibly go and then leaving a remaining probability there on that space. And so I basically had to do that for every row of my transition matrix where you could possibly end your turn on a chance or community chess card. So once I did all of that, I then moved on to my initial state, but it's important also to mention that I had to make a couple of assumptions within that transition matrix. The first is that the deck is always reshuffled after a community chess or chance card is drawn. The reason for that is it makes the probabilities independent of one another rather than having to deal with conditional probabilities. The second thing that I assumed was that a player immediately pays $50 to get out of jail before their next turn. So then once I moved on from that to my initial state vector, I ended up finding that my initial state vector was B0 equals 1, 0, 0, 0, all the way up until column entry 41, which is also a 0. The reason why this is our initial state vector is because you start the game on go, and you cannot be anywhere else at that point in time in the game. So I then went through the Markov chain and found that this did in fact converge, and I then verified it once again using eigenvalues and eigenvectors, and this is the steady state that I ended up finding. So basically, I know there's a lot of information going on here, but the numbers on the far side, 1, 2, 3, 4, all the way up into 41 is just representing the spaces, and then next to that, that's their actual label name that's on the board game itself, and then the numbers that are next to those, these here, are going to be the probabilities that are actually associated with landing on that specific space. So there's a couple of things that are really important to notice here. The first is that not all of these probabilities are the same, which means that it's not equal, that every space on the game board is not equally as probable to land on as others. The next thing to realize is that unlike the Chutes and Ladders game, not all of these spaces converge to 0 where everything's just landing in one particular state at the end of the game, meaning that the board game itself in Monopoly is a continuous game. It's only the additional rules about money and things like that that actually in this game. The board itself is continuous. So I went ahead and verified this a third time using a simulation of the Monopoly board in MATLAB with the help of Dr. Meek. And what I ended up finding with a very large N, where N represents a large number of turns, is these are the probabilities these are the long-term probabilities that you would find if you were to continually go around and around the Monopoly board. So we can see that these ones are very similar to the ones that I found myself. They are similar up to at least 3 decimal places, which is really good. So then I went ahead and reordered this for you all to the most probable spaces to land on to the least. So what we can see right off the bat is that just visiting an in-jail, you'll land on that 6.76% of the time, which means every time that you take a turn, you can expect that 6.76% of the time you are going to land either in jail or just visiting jail. Now that doesn't really seem like a lot, but you have to keep in mind that we're breaking up a probability of 1 into 41 different spaces. And as you can see, the next most probable space to land on only has a probability of 3.19%. That means just visiting an in-jail is more than 2 times as likely to land on than any other space on a turn. So what we can see, the most likely property that you're going to land on in the game is Illinois Avenue. That's followed by New York, Tennessee, Kentucky, and St. James Place. So what we see happening is a sweet spot occurring within the game around the free parking space. A lot of this is due to the fact that just visiting in jail is the most likely place to land, so you're constantly getting put back on that half of the board. This is really important when you're in the actual gameplay because this can help you decide which properties you actually want to buy or trade for. Because if you have a property that is more probable to be landed upon, you're more likely to generate more revenue. So other than just looking at the most probable spaces, I also went ahead and looked into expected returns. An expected return is the amount of revenue a player can expect to receive on any given player's term. And this basically becomes the summation of x times the probability of x, where x represents the revenue generated by another player landing on the given property, and p of x represents the probability of landing on the given property. So I did this for every property in Monopoly, and these are the results I ended up finding. And so basically what we see is that expected returns is telling us that if we wanted to own a monopoly and we didn't want to put any houses or hotels on it, then the best property to do that with is the best property set to do that with are the greens, Pacific, North Carolina, and Pennsylvania. If we are just looking to put an additional house on a set, the best property set, once again, to do that with is going to be the green properties. And that goes all the way up until 3 houses. And it only switches when we want to put 4 or 5 houses on. Once we get to 4 or 5 houses, expected returns dictate that the best property set, the most profitable property set to own for that would be the orange properties, St. James Place, Tennessee Avenue, and New York Avenue. And then if we look down at the railroads, the most profitable railroad to own, if you're only going to own 1, would be B&O. If you're going to own 2, that would be Pennsylvania and B&O. And if you're going to own 3, it would be Reading, Pennsylvania, and B&O. Now, similarly, if you wanted to own one of the utility or waterworks companies, the best one to own for that, the most profitable one to own, would be Waterworks. Now, expected returns really only look at the benefit side of owning a property. So I also wanted to do a calculation that looked at the cost side of owning a property set. So I did break even, where break even is the number of times another player would have to land on each property with or without houses or hotels in order to pay it off. So I did this once again for every property, and these are the results I ended up finding. Where if you are going to own a Monopoly set, but you don't want to put any houses or hotels on it, the best one to own for that is actually Park Place and Boardwalk. If you have already paid off your property and you want to put a house on, then the best property set to own for that would be the orange one, St. James Place, Tennessee, and New York. And then if you want to own 2, it goes back to the dark blues of Park Place and Boardwalk. If you want to own 3, the one that's going to pay itself off fastest is going to be the orange properties again. And then if you go up to 4 houses or a hotel, then the property set that's going to pay off the fastest would be the light blues of Oriental, Vermont, and Connecticut. And if we look down at the railroads, we see that the railroad that's going to pay itself off the fastest would be B&O. And with 2, it's going to be Pennsylvania and B&O. And then with the utilities, Waterworks once again is the best. So the last thing I looked into is marginal utility, where marginal utility is the additional satisfaction a consumer gains from consuming one more unit of a good or service. Marginal utility is then the total utility of the additional revenue gained by adding an additional house or hotel to a property set. I then use the law of diminishing marginal utility that states that as a person increases consumption of a product, there is a decline in the marginal utility that person derives from consuming each additional unit. So basically, I use this to determine how many houses you really should put onto a property set. And using this graphic here, we can see which ones, where you should really stop. So on the x-axis, we have the number of houses or hotels, and on the y-axis over there, we have the total utility. And basically, we have the property sets just going up. So this would be Mediterranean and Baltic. This would be the light blues. These would be the pinks, the orange, the reds, and all the way up until the very top ones, which are the dark blue properties. And what we see when we do this calculation is we're really looking for the largest slope. Where is the largest marginal utility occurring within the game? And when we do that calculation, we find that for every property set besides Mediterranean and Baltic, that's going to occur at 3 houses. So the best number of houses to put on a property set is actually going to be 3. If you own Mediterranean and Baltic, the best number to put on is a hotel. You want to build that up as fast as you can. That's the best way that you can get as much revenue as you can. So in conclusion, if there was more time, I would want to investigate the trading aspect, short-term benefit versus the long-term cost. And then I'd also want to look into some common rule changes of monopoly, such as free parking, trades that involve free passes, and not building uniformly. So in conclusion, the important theories were the Markov process, which allowed us to figure out the probabilities of each space, expected returns, which allowed us to look at the benefit side of owning a property, break even, which allowed us to look at the cost side of owning a property, and the law of diminishing marginal utility, which allowed us to figure out how many houses you should really put onto a property set. And that is my project. Thank you all so much for listening. Are there any questions? I know we're a little short on time. Yes, ma'am. Okay. Any? Yes, sir. Yes, sir, they are. Yes. A Markov process, though, does actually follow just one player. So I'm not 100% sure how I would go about adding that part in, but yes, that is something that I really did want to look at, how additional players affect the overall game and how that affects which properties are better than others. Yes, ma'am. I sure can. Yes.
So if you were to play Monopoly tomorrow, would you try to get to that corner where
free parking.
Free parking, and then try to buy that up, and then put around 3 houses on each corner? Would that be a pretty good strategy? Or?
Yes, that because those spaces are more probable to land on, that does make them somewhat better. You do have to keep in mind that, of course, the other properties like the greens and the blues can generate more revenue, but since those ones are more probable to land on, you're more likely to get more revenue from those. So if I was playing, yes, that would be my strategy, is I would try to take up that corner and build at least 3 houses. Any others? Yes, ma'am.
So your simulation, those the probabilities in the steady state vector, those are long-term probabilities, right? If I play for a really, really long time, what do you think the difference might be, kind of considering a short game?
Right, so the difference between it is those are, in the actual gameplay, the probabilities that are associated with every single turn, they're not going to always hold to what those long-term probabilities are, so you can't expect that every single time you take a turn, you're going to land on just visiting or in jail 6% of the time. That's not what that's saying. That's saying that in the overall game, to where you can build a strategy, those are the probabilities that you want to deal with. But when you're playing the actual game, those probabilities may not hold in the short term. Yes?
How many turns did you play for your simulation?
50 million. So it takes a really long time for that to stabilize. If you only do 10 or so, it's not going to be anywhere close to what's in my Markov process.
Have you thought about where that point, that 3
I believe that it actually comes from, I actually found it within the simulation as I was doing it. It comes from the fact that there's a really, really small change where if you're on chance, there's a particular case where you're on chance that that you could possibly draw a card that takes you 3 spaces back, and that 3 spaces back could possibly take you to community chest. This would be where you're dealing with, if this one is right here. So if we're looking at this one is occurring right here. So we have this chance, and if you're at this chance, there is a very, very small probability that you could draw a go back 3 spaces card, which will then send you down to community chess. So I had a small error, I guess, within my Markov process where I didn't consider this part of it. So basically what you would have to do is once you get sent back to jail, now you have to redraw a community chess card, and then that redrawing of a community chess card then changes that probability where you could possibly be sent to either go or to jail. And so that is something that I hope to fix in the coming weeks. Okay, thank you all so much for coming and listening to me.